2 experiment title measurement of coupling losses in optical fiber using alignment model. We'll continue. Now you can see we have this fiber 1, this is another fiber, and if we have a gap between these two, the gap is called as end gap displacement, which is measured in terms of millimeter. Now you can observe, if there is a displacement with respect to this center axis of these two fiber, then we say it is a lateral displacement, which we can measure as in millimeter. And angular displacement, if we have angle variation or deviation compared to first fiber and second fiber, this is angular displacement. So what we will do, we will first do end gap displacement. For that purpose, I have made one simple table. Please focus over here. Now in this table 1, I have written this end gap displacement as a d distance, right? I will have 3 millimeter or 4 millimeter. 3 millimeter is my default, and for that we have just calculated output is about 0.15 volts. Now what I will do, by using this screw, I will increase the displacement and I will make displacement by 0.25, right? So for that 0.25, I have added that 0.25 in that 3 millimeters. In that 3 millimeters, I added 0.25. The distance now became 3.25, and for that I will measure the output, and now my output is 1 division, 2 division and 3 division itself. So for this there is not that much change, so I will write the same value. Now I will further increase, I will increase by 0.25 again, and now my distance became 3.5 millimeter. Now I will observe its output. Let me adjust it. Okay. So it's 1 division, 2 division and about 2.4 divisions. So my output for this is 2.4 divisions into my 50 millivolts. So after calculating this, the value will come, which will be probably less than this, and 2.4 into 50, if I calculate it out, so if I multiply 2.4 divisions multiplied by 50 millivolts, which comes to 0.12 volts. Now again I will increase this lateral displacement, end gap displacement, and I will make this D equal to 3.75 millimeters, and now I will calculate output voltage for that 7.3 millimeter. Let me adjust it. It's coming about 1 division, 2 division and 2.2 divisions. So it's 2.2 divisions into 50 millivolts, that is equal to about 1 volts, is equal to 0.11 volts. Again I will increase and I will make lateral displacement to 4. So this will become 4 millimeter, and now 4 millimeter, my output is about 2 volts peak to peak. So 2 into 50 millivolts, my output is 0.1 volt. So going on like this, I will increase to 4.25 millimeter by adding another 0.25 into this. Now I will able to see my output is almost same value. Let me add more. So this became 4.5 millimeter. At 4.5 millimeter, my output is less than 2 divisions. So it's almost 1.8 divisions. 1.8 divisions into 50 millivolts, and that value probably comes to 0.9 volts. So if you observe, if you observe, as I increase this displacement, the spread of light which was coming from that side is being less coupled into the another fiber, and so that the output is falling as my in-gap displacement is increasing. Okay. Now we will measure how to calculate the loss when there is a lateral displacement. Now at the moment my both fibers are connected in the center of its axis, and so that lateral displacement at the moment is 0 millimeter. So there is no deviation in laterally. By using this screw, I can adjust the lateral displacement by 0.25 millimeter. So what I will do, either on that side or this side, I will move this module by 0.25 millimeters, and I will calculate it down the what is the output corresponding to that value. It will give me lateral displacement. If either I move this side or this side, lateral displacement will remain going to same. In this case, objective is that if we have two circles, and just if I imagine this two circle, if I in my hand like this, right, one cross sectional area of a fiber, another cross sectional area of fiber, and if I move something like this, this is something called as lateral displacement. If you observe it, if I am moving it like this, there will be lateral displacement. When they are in a center, maximum amount of power from one fiber is going to be coupled into another. If there is a laterally displacement with respect to axis, then there will be less amount of power from one fiber to another fiber will be going to couple. This also by the means of this we can able to also calculate a numerical aperture that we will study in next experiment. Let's see here. Now I am going to increase by 0.25. My default value is again for 0 lateral displacement, my output is 1.5 volts. Now if I increase to 0.25 lateral displacement on that side, so my output still remain in that range. Now my output is about 2.2 volts, 2.2 divisions into 50 millivolts. So for 0.25 millimeter, my output is about 2.2 into 50 millivolts, which comes to 0.11 volt. Now I will increase this to 0.5, precisely 0.5. So for 0.5, my output is about 2.5 millimeter. My output is about 2 into 50 millivolt, which is about 0.1 volt. Then I will increase further to 0.25. At 0.25, my output is about 1.8. 0.25, that is 0.75 millimeter. My output is 1.8 into 50 millivolt, which comes to 0.09 volts. Further I will increase and I will make 1 millimeter deviation, which is, and probably at that instance of time my output measurable, it's almost 1.2 into 50 millivolts, which is very less, and that comes to 0.06 volts. And now if you observe, if I go on increasing it further, it's almost one division into 50 millivolt, so it's about, that is 0.05 volts, that is 50 millivolts itself. And if I go on increasing at about 1.5 volts, 1.5 millimeter, I am not able to measure that. I mean, another way I can say I almost reach to the end of the fiber. So you can observe, as I move two fibers laterally, the output is decreasing, and that is something called as lateral displacement loss. Okay, so by this we can calculate a table, we can do a table. Distance versus lateral displacement. Okay. One type of loss is a bending loss, or you can say angular displacement with respect to two fiber ends. So there is an angle is given, please focus over this. Now I am making angle of 5 degree. I assume that the 3 mm is default here, but now I increase angle by 5 and it's observed that my output is decreasing, and now my output is almost 1.5 volts for 5 degree displacement. It is 1.4 divisions into 50 millihertz, which comes to about 0.07 volts. Then I increase this angle by 10 degree, and now it's went into almost noisy level, so I am not able to measure, because this 10 degree angle itself losing lot of light, and that is not going to be coupled into my fiber, and so I am not able to measure it. Or if I say it's almost reaching very low 1 division into 50 millivolt, so it's almost 1 division into 50 volt means 50 millivolt output I am going to get. So this angle makes lot of okay, by using this model we can increase the angle like this, right? So for this fiber, the at 10 degree I am not able, this is a scale, and there is a notch is given here. If you able to observe, notch is given here, and that notch I am adjusting to either 0 degree, 5 degree, 10 degree, 15 degree, 20 degree, something like this, right? And so it's observed from this that if there is an angle between two end of fiber, there will be loss. After performing experiment in lab, we have taken the readings for end gap displacement, where end gap we have varied from 3 mm default value to 4.5 mm its maximum value, and we have observed and measured the output voltage coming across it. And after calculating these values, we have plotted the graph. The graph clearly shows that as end gap displacement increases, the output from one fiber to another fiber, coupling between one fiber to another fiber, also decreases. So the relation simply says that if end gap displacement increases, coupling also decreases. In second type of displacement, that is lateral displacement, here it is shown on two sides. Above indicates negative while below indicates positive. It's just matter for indicating lateral displacement either on left side or right side. So at middle, when both the angles of the fibers are coinciding with each other, or they are aligned, the maximum output we are receiving at about 1.5 volts, and as we go away from the axis, the output starts decreasing, which is clearly shown in the graph. If you see in the center, our output is maximum, but as we move laterally either left side or right side, our output is decreasing. The third observation, we found that if we have made an angle between two ends of fiber, our output is also decreases, and this indicates we have calculated initially for 0 angle, that is both axes are coinciding to each other and there is no angle between them, so we got a maximum output at that point, it's 1.5 volts. But as soon as we increase to 5 degree either left side or right side, the output decreases to 0.07 volts. So the relationship between end gap displacement, lateral displacement and angular displacement, you can simply observe that if end gap displacement or lateral displacement or angular displacement increases, our coupling of power from one fiber end to another fiber end also decreases. The conclusion of this experiment, we have used a alignment model to find the coupling losses are affected by end gap displacement, lateral displacement and angular displacement between two fiber ends, and we have plotted a graph between displacement and coupling losses. Thank you.